We continue with the exercises for 1.4, section 1.4. I believe this is exercise 1.4.3. Has to show that the intersection where all ends in end of the open intervals 0, 1 over n is empty. It's the empty set, so this doesn't contain any element. And they actually make the point here they point out to you that this actually demonstrates why you need to assume that the intervals in the nested interval property are closed. These intervals here are open, so these intervals are open and they're nested. One is contained in the other, each one contains the next, and so on. However, the intersection is empty. Okay, so this is why we need the hypothesis that the interval needs to be closed. The intervals involved need to be closed. So why is this? So let's quickly over the proof of why this is indeed the case. Well, we're going to show that in fact there is no element in this intersection. Okay, so in fact we're going to show I don't want to write it as a contradiction. So let's notice. So the first thing is to notice that the intersection of n in n of the intervals 0, 1 over n are all contained in 0, 1. Right, 0, 1 is the biggest of all these intervals. And so if there's a candidate to belong to the set, then there has to be a number between 0 and 1. Right? So now we let x be any number in order to just write as epsilon. This number between 0 and 1. So we have a number epsilon greater than 0 and smaller than 1. And we want to show that that number does not belong to this intersection. I'm writing it as epsilon on purpose. So what do I say now? So by the, are you guessing now? The what property? Yeah, it is the Archimedean. By the Archimedean property, there exists some n in n such that 1 over n is smaller than epsilon. Remember, the epsilon is positive since it belongs to 0, 1. Okay? But this implies, but then this implies that epsilon does not belong to the interval 0, 1 over n. So this implies epsilon does not belong to the interval 0, 1 over n, because epsilon is in fact greater than 1 over n, so it does not belong to this interval. right? But this interval contains this intersection. So if it doesn't belong to a set that contains, okay, maybe I should use a different notation here. Well, I mean, I guess you understand what I mean. So this is here on this side, n is a dummy variable. Here, this is the n that we found by the Archimedean property. I should have named it perhaps n naught. Okay, that makes it better. So this contains this intersection. So this lies outside of a set that contains the intersection. So that means certainly that epsilon does not belong to this intersection. So no, the conclusion here is that no number greater than 0 belongs to the set. And 0 does not belong to the set because this intersection here does not contain 0. Right? No, none of these sets here contains 0. So we've shown that epsilon, if you pick any epsilon, it cannot belong to this intersection. So that means that we have no options, and so this implies that the intersection has no elements, and hence is the empty set. Which is exactly what I wanted to show. Okay, so this is the next problem in the series. So we've characterized, again, the supremum in a different way in the previous problem. And now when we use the Archimedean property, now we're using the Archimedean property again to show that this intersection here is the empty set. Why do we need to have a closed interval? Because here, if the interval included, say, 0, then 0 would be in the set. So if instead we had we're taking the intersection of these sets, then 0 would belong to the singleton 0 here would belong to this intersection. So where does this argument go wrong, you may ask? Why is it that by simply adding 0 to all the intervals, you make you have now an element? So this is clearly then not the empty set. You found a number, which by the way is the only number this intersection can contain. Okay, so what is then, why is there no contradiction with the argument we just used? So I'm going to give you a couple of minutes to think about why this is. This is the proof. Read it carefully, take a look at it, and tell me, why can't we just apply the same proof to this intersection here and say that this intersection is at the empty set as well? Okay, well, if you thought about it, well, great. If not, I'm gonna explain to you why now. The reason is this. Epsilon is greater than 0, but how this, where do we actually use that? We apply the Archimedean property. The Archimedean property works only if epsilon is greater than 0. If epsilon is greater than 0, then you can find an n naught such that 1 over n naught is smaller than epsilon. If epsilon is equal to 0, so if we were given an epsilon, 0 is part of the set, so part of the possibilities, we would not be able to apply the Archimedean property, because the hypothesis is that you have a number which is positive. Then you can find a number n, since the 1 over n is smaller than that positive number. So this is where the proof breaks down. And to see explicitly why you need this, or why is it that you need to include you need to consider only close intervals. Well, it's because of this kind of situation where you have one of the endpoints, if it belongs to the set, then maybe that will belong to that endpoint will be the intersection. Technically, as I said, it's because we cannot apply the Archimedean property in this case. And the reason why this works is because 0 belongs to every set. If you close one of the endpoints. Okay? I hope this is more clear now. We'll continue that in the next video.